We concluded the last class on hydrogenation discussing catalytic processes that proceed via monohydride intermediates. An important manifestation of this reactivity is in the reduction of carbonyl compounds, particularly the enantioselective reduction of carbonyl compounds. And so I'll illustrate that by going through one specific example. This is one of the Naori family of catalytic asymmetric reductions. And so this process begins with a ruthenium, typically a dihalide precatalyst. Just in the interest of time, I haven't drawn this out, but that this PP refers to a bidentate bisphosphine ligand. Here, one example of that would be binap, and S just refers to solvent. Typically, this reaction is performed in alcoholic solvents. And so the reaction begins with a catalyst, with activation of the precatalyst, typically done in the presence of base. Oops. And then the active form is this monohydride drawn. Coordination of, in this case, a 1,3-dicarbonyl. And here you see again the importance of directed reactivity. I think that's a common theme in the early hydrogenation literature, particularly in enantioselective variants. Substrate directivity plays an important role in rigidifying and reducing the intermediates involved and reducing the number of conformational degrees of freedom as an important element of stereocontrol. So the 1,3-dicarbonyl can coordinate, displace two molecules of solvent. And now your hydride, which, remember, metal hydrides, as we've talked about, can have a range of reactivity from being protic in character to hydridic in character, and this ruthenium monohydride is hydridic in character, so it's able to reduce the intramolecularly tethered 1,3-dicarbonyl. If you want to push arrows, you can do so like such. That establishes now this stereocenter. You have a step where you will coordinate a solvent molecule, and here you can facilitate ligand exchange through intramolecular proton transfer. And then exchange off of the product for additional solvent molecules, followed by regeneration of the propagating monohydride. So I'll zoom out. I'm going to go through this quickly, so I'll zoom out in case you wants to jot that down. And we'll then take a peek at a related example from the modern literature that illustrates some of these same reactivity principles, but in what I think is an interesting way. And this brings us to our chemist of the day from last time, from day 9. I don't know if anybody recognized the photo and wants to shout out the name or post it in the chat window. We had this individual as a speaker, but I think it might have been before the time of many of the students here. So let me just pull up that sheet very quickly. I'm not hearing any takers.
That new Charles at National University of Singapore.
Very good. Was that Win?
Yeah.
Thank you. Win, and I can't remember. Did you go to NUS or you went to Nanyang?
I went to NTU.
Oh, and NTU. Okay, sorry. Okay. So this is Yu Zhao. He's a former trainee of Hoveda and Schrock, and has been independent for, I think, just short of 10 years now, and established a really vibrant career that spans different aspects of metal catalysis, including CC bond forming reactions as well as stereoselective reductions. And so here's an interesting example. Again, let me zoom out. where the substrate is this homoallylic alcohol shown. We have a chiral rhodium catalyst generated in situ from ligation of the ligand shown L star and this rhodium precursor. And we've got a series of steps that needs to take place where essentially the H2 equivalent from the secondary alcohol is transferred to the alkene. And so let's walk through how that might take place, and I'll enlist the help here of some volunteers, or maybe one volunteer to get us as far as we can. What do you think here, Eleanor? So I've drawn this substrate coordination step, and then what could happen next?
I'm not sure. So you don't have a rhodium hydride here.
You don't have a rhodium hydride, but we're in the hydrogenation section. Maybe I'll zoom in and draw this in a slightly more suggestive way. Let's see if that triggers any thoughts.
Sorry, I'm not sure. So I know like eventually you have to oxidize there. So you're going to use that hydride.
Okay. So you do know, you're just slow playing us. Okay. So here we can draw a transfer of this hydride, as Eleanor said, to the metal center. So now we've generated our metal monohydride in situ here from oxidation of our secondary alcohol. And then what might happen next, Eleanor?
Oh, sorry. So now can the hydride add to your alkene?
Beautiful. And where would it add, do you think?
I don't know. Maybe the terminal position?
Yeah, I don't know is a good answer because it's not necessarily obvious. You're either going to have to make a tertiary alkyl metal that's benzylic and so maybe is sufficiently stable, or you're going to make the more primary alkyl metal. And so if you're not sure, I think that intuition is good. Let me draw it as you described it, which is add at the terminal position. Is that right? Let me draw this with not as bad of bond angles. Okay, and then I'll just fill in this detail here because it's a little bit, I don't think you'd know this unless you were in some mechanistic studies, but they find then that this can undergo further isomerization with these acidic protons here, or reactive protons, to put one of these hydrides on the metal and generate what is a I made this mistake of not drawing this big enough. So now essentially you just get I've drawn this in 2 steps, but essentially a migration of an H atom from the alpha position to the beta position to generate a rhodium enolate, which then can undergo protonation as you would draw a metal enolate to close the cycle. Okay, some stuff there that maybe looks a little bit exotic, but hopefully builds on principles that you've seen in a reasonably logical way. Any questions on that? Maybe I'll just quickly highlight these in color so you can see where these atoms are going.
Can you just quickly restate the selectivity of why you end up with the rhodium adding in a tertiary position and the hydride going to the primary? For the first shift that you get.
Yeah, as I said, I don't know that you would maybe expect this a priori, or you have at least competing arguments to go one way or the other. So I think in terms of the mechanistic studies that they run in this paper that I think I cited up here, it's consistent with this model. You could draw it the other way, and that wouldn't be unreasonable.
Okay.
If you were just looking at it for the first time. But certainly the benzoic stabilization is important, and you might not draw it that way if it wasn't for that aryl group, and indeed this reaction is actually restricted to substrates that do have that aryl group present, perhaps for this very reason.
Okay, thanks.
Yep.
Sorry, Kiri, is the hydride getting added on the opposite face of coordination? I guess like as the methyl group is drawn up, is there a way to rationalize that facial selectivity?
Which hydride?
So sorry, I guess the final product, like how would you be able to predict like if that methyl group is going to be up or down?
Yeah, I don't think there's a straightforward way to predict it from okay. First principles. You'd have to think about how this ligand is going to bind.
Okay.
I mean, often I would say, except for maybe the most studied asymmetric, catalytic asymmetric reactions, that there aren't convenient mnemonics for sort of predicting the absolute stereochemical outcome from an arbitrary substrate, sure. If that makes sense.
Okay. Yep. Thank you.
Okay. The last one of the last things I'll cover before turning the floor over. I know Tanner chomping at the bit are reactions that proceed via outer sphere pathways, and where the metal plays more than just the role of cheerleader. Here, the metal is intimately involved in the action, and these are reactions that often involve what's called metal ligand cooperation or cooperative catalysis. So here's an example using this very interesting complex structure that in solution actually breaks up into two constituent forms. I really like this this example. So it's a bridging dihedride that breaks up into essentially an H2 donor and an H2 selector acceptor in solution, and this is called the Schwo catalyst, very commonly used in carbonyl racemization. Why would you want to racemize carbonyl compounds? You might ask. And this is powerfully used in dynamic kinetic resolutions as just one example. So this dissociates into an H2 donor and an H2 acceptor. In the H2 donor, I'll draw those, highlight the H2 equivalents here, so that's crystal clear. The H2 donor can reduce carbonyl compounds. So you have now a OH bond, which is protic in character, delta plus, and then a ruthenium hydride, which is delta minus in character. And this can reduce carbonyl compounds or imines equivalently through a transition state that looks like this. And I've shown this as just one example of what is really a common reactivity paradigm, and also manifests itself in other members of the Noyori family of reductions, notably these examples that contain diamines that have an NH bond present. And so as these, I won't cover this in detail, but I encourage you to take a peek at this in the textbook. As these reactions proceed, they also generate a metal hydride. So I'll just draw that here, superimposed in a different color so it's clear. And then now you indeed get this same embedded H2 equivalence where the H2 is stored across the ligand and the metal and can be selectively delivered across a carbonyl compound. So this is nice because the metal and ligand can play cooperatively in a way that where the polarization of the hydride and then the proton is nicely aligned to the fact that the substrate is also polarized, right? Okay, and then there are some other, this got mixed, all screwed up when I was moving things around. There are other types of hydrogenations that we won't cover in the interest of time, those that involve radical processes. This is, of course, a radical reduction, radical H atom transfer reductions, of course, topic near and dear to the heart of this department. There are reactions that proceed via sigma bond metathesis, and sigma bond metathesis reactions most typically involve D0 metal. Here, the metal does not have d electrons, so it can't readily participate in oxidative addition, and that's a hallmark feature of sigma bond metathesis type pathways that typically involve a metal hydride, where the metal is in the lanthanide series most often, or a metal alkyl. And then bimetallic processes, as we covered from as one example earlier in class, in the bimetallic oxidative addition from the likes of Neil Mankat and others who've worked on this topic. Okay, and now I'm going to just conclude by showing some key milestones in asymmetric reductions. We talked about how Knowles early on had worked with these chiral at P phosphine ligands, but these are disadvantageous because they're not super easy to make. You can't make them in a modular way. And so a key breakthrough was from Kagan, who reported this first example of a C2 symmetric ligand, ultimately derived from tartaric acid in this case. And then Knowles took this idea and ran with it and developed a C2 symmetric version that was also chiral at phosphorus. And as one interesting note, this dipamp ligand hydrogenation system was used in the seminal study by Halpern, which I think is the archetypal case study for a reaction that proceeds under curtain hammock control. This is one of Donna's, I think, favorite papers of all time, where you have fast and reversible substrate binding and the minor diastereomeric substrate metal complex reacting faster in the productive oxidative addition, reductive elimination step. And then later, Noyori's beautiful binap structure that I think, as you can appreciate just from the fewer numbers of sp3 hybridized carbon atoms, is much less rigid, much less flexible and more rigid. And I think it had a transformative impact on catalysis. So this is highlighted. There's more information on asymmetric in your handout, so I direct you to that. And here is just some key synthetic applications. From Monsanto, oops, where they used this dipamp system of noles. This is, it's fair to say that the reaction that got Knowles the Nobel Prize. This was used in their commercial synthesis of L-Dopa. And then Takasago, they've had a long-standing collaboration with the Noyori group over the years, and you probably in classics covered menthol synthesis. It's in, I think it's covered in classics, the classics 1 textbook. That's actually not a hydrogenation, but is a isomerization, and so in that process is a little bit more complex. So one that illustrates the same principles, but is a little more simple is shown here. Synthesis of citronellol, which can be accessed in one step by stereoselective directed reduction of geraniol. Okay, I already took more time than I told Tanner I would, so now I'll stop there. I went through that quickly, so please don't hesitate to follow up with me or the TAs if there are questions on that, but we do want to keep moving forward until we have enough time to cover carbonylation chemistry.
Great, I muted myself. Okay, so let's jump right in as we only have an hour. Today, as Kiri told you, we're going to be talking about carbonylation chemistry, which blends in nicely with hydrogenation, as many of the intermediates are similar or the same. And one of the reasons I really like these reactions is you can essentially take these crude elements, carbon monoxide, hydrogen, water, and alkenes, so like earth, wind, fire, and water, and make some pretty interesting commodity chemicals as well as designer compounds. And so I like to think of this as the kind of chemistry you would do if you were stranded on an island somewhere in the Pacific, assuming there was a volcano to provide some carbon monoxide and an asteroid that crashed into it to give you some rhodium and all the other resources you would need. And so one of the most interesting aspects of carbon monoxide in the sense of these reactions is that it's, and others, is that it's almost completely inert to most reaction conditions you would run as far as organic reaction is concerned. And that gives really good chemoselectivity in that you're able to prevent any background reactions where CO would be reacting directly with your organic reactants, and these processes are so efficient. I imagine things like CO2 are less innocent, and nucleophiles such as primary amines can just directly attack them. And so in this sense, CO is in many ways an ideal source. And so assuming on your way to Pacific Chem, you ended up stranded on this island somewhere in the Pacific. You got your CO from the volcano here. maybe some ethylene from a ripening banana, and your rhodium from the comet. However, you need some hydrogen. So the first thing you're going to want to do is this, what is called the water gas shift. And this is a convenient way to take water and carbon monoxide and convert it to CO2 and H2. And in most cases, and in these contexts, certainly this is going to be done to produce H2. And so, although this process is normally done in a heterogeneous fashion, it is viable with homogeneous catalysts such as these homoleptic metal carbonyls, among other. And this is typically run like in aqueous basic conditions, as you'll see here. So briefly, we'll go through the mechanism. And I'm just gonna call on people in order from the way I see them in the Zoom format. So hopefully we can get some participation. However, if you really wanna just jump in and shout out the answer, feel free. So I guess the first one is Tsuhan. What is the first intermediate we have here going to be? If we take, let's say, tungsten carbonyl, and we add, and we're heating this under an aqueous basic solution.
So I guess the hydroxyl group will attack the tungsten.
Perfect. And so that leaves us with now this anionic tungsten center that has a formal unit on it. And so now that we have this anionic tungsten center, it will react with a further equivalent of water. And what do you think it's going to make next, Sunhan?
So because there's a negative charge, so maybe it will deprotonate the water.
Perfect. So now we will have a tungsten hydride and this formal unit. And so take us home now. How are we going to get to making CO2 and hydrogen? What steps are going to be involved here?
So I guess the OH of the carboxylic acid, the proton will shift to the tungsten, then there will be a CO2.
Perfect. So this is a decarboxylation reaction. And from the beta position, so similar to the beta hydride elimination, we'll get rid of the CO2 and form this tungsten dihydride, which then can just simply eliminate H2. And so this reaction, as the name alludes to, is in equilibrium, as it's called the water gas shift. And so simply changing temperature and the quantity of certain reactants can shift it one way or the other. And so depending, typically you want to favor hydrogen production. And so typically high heat makes this reaction go faster to forming hydrogen. However, although it goes faster, if starting from water and CO, it's typically at high temperatures favored to actually be H2O and CO. And so simply just changing the reaction conditions or consuming one of the products can shift this reaction. Okay, great job, Tsuhan. So now we have some hydrogen and we can do all the chemistry we would ever want. And so next, we're gonna move on to one of the, I guess, seminal examples of carbonylation chemistry in industry, which is the Monsanto acetic acid process, and then the later developed BT Cativa process. And so, as you might imagine, acetic acid is a commodity chemical, and I guess in 2014, 17 billion pounds of it was produced worldwide. So it's a pretty high demand compound, and of that 17 billion pounds, approximately 80% of all acetic acid was produced using either Monsanto, BP, or another equivalent process. And so this is sort of the main way that we produce our acetic acid. And this reaction was discovered by BASF in 1965. And you'll see this name BASF throughout this lecture as they sort of pioneered much of this chemistry. And in the initial report, they used a cobalt catalyst with some iodine additives under these pretty forcing conditions. And then they were able to get at least mild catalytic efficiency, however, not quite what you would need to make it commercially viable. A few years later, however, Monsanto discovered that rhodium was also operable in this process and could operate at catalytic loadings at least 100 times less and at much milder conditions, making the design and operation of such chemical plants much more realistic. And so with that, they started the production of acetic acid in what is now known as the Monsanto acetic acid process. And this process is quite straightforward, where at least from a organic perspective, is you simply just take 2 C1 units, methanol and CO, heat them up with your rhodium catalyst, and out you get acetic acid. And so from a convergent synthesis point of view, this is pretty ideal. And so the main workhorse for this reaction is this simple rhodium catalyst. And although other rhodium catalysts with more fancy ligand designs may be operable, because this again is a chemical or industrial process done on massive scale, ligand cost and recovery is a huge concern. And so if you can do things without ligand, it's greatly preferable. And so in this case, these anionic rhodium species are the active catalysts. And so let's see who's next. Brendan, do you want to help us out here with the electron count for this rhodium complex?
So is it D8, rhodium 1? It's anionic, and then should be. Would it still be? It'd be 18 electrons, right?
18. Why do you say? Oh, sorry. Why do you say 18?
So you have a D8, and then you have 4 2-electron ligands, but then you have the negative charge there. So does that count?
So
It's either 16 or 18.
So these types of square planar rhodium 1 species form 16 electron complexes. But yeah, okay, and the coordination number here, I sort of just gave it away.
It's 4.
4, perfect. Okay, and so these simple rhodium catalysts actually perform quite well and have been studied with a great deal of mechanistic detail. And so in this sort of witch's brew, in addition to methanol and CO, you typically will also have an iodine promoter, which is added in the form of elemental iodine or iodine salts, such as just lithium iodide. And so in this reaction process, you're going, as you would imagine, you want to use the cheapest materials process and potentially generate your catalytically relevant species in situ. And so this process is initiated by the reaction of HI with methanol to form water and something else. So Camille, do you want to tell us what we're going to get if we heat up HI and methanol?
Methyl iodide.
Perfect. And so, as you know, methyl iodide is not necessarily the cheapest thing to buy in a bottle. And so it's much easier and commercially viable just to generate it in situ by this reaction. And so now, Camille, can you help us out? The methyl iodide will react with this anionic rhodium species to form
Does the CO insert into the methyl right away?
Not quite. So first we have a rhodium-1 species here, and we have an anionic rhodium-1 species here, and we have a pretty good electrophile. So what else could happen in this case?
You just form a rhodium methyl bond.
Perfect. And so in addition to forming the rhodium methyl bond, how is that going to affect the rest of the complex and the oxidation state?
Are you doing oxidative addition of the methyl iodide?
Perfect. And so we actually will get this trans oxidative addition complex, which we'll go through and mechanistically in more detail in a little bit. And so now that we have this rhodium-3 methyl complex, now this can be intercepted with another equivalent of CO to give the complex you referred to earlier, where now we have CO inserting and to close the catalytic cycle, Camille, what are we going to do here to generate our starting rhodium complex?
I think we'll have to add water.
This is okay, so this is one possibility. Camille suggests we add water. So how would water add to this rhodium complex here?
I guess it would give you acetic acid. And then you'd get
And
HI.
And HI, perfect. And so this is one possibility. We can get regenerate our HI here, as well as acetic acid. However, imagine that before water can attack this complex, you get a unimolecular reaction of simply just things already in the coordination sphere of this rhodium center. And so if you were to envision that, what do you think you would get?
Do you do reductive elimination to form the I? Yeah.
Perfect. So you do direct reductive elimination of the rhodium acyl species with the iodide to form this acyl iodide, which, as you would imagine, is pretty quickly hydrolyzed by water to give acetic acid and HI. And so this process is mechanistically quite interesting, and this final step can be changed based on your exact reaction conditions. And as you would imagine, if you have more water around, you may favor more direct formation of acetic acid, while as more anhydrous conditions can favor the direct reductive elimination to form the acyl iodide. And so these processes are highly dependent on both the concentration of rhodium and methyl iodide, as methyl iodide oxidative addition is proposed to be rate limiting in these cases. So you would expect it to be greatly affected by both of these. And while these processes are not inherently as dependent on the CO concentration as other carbonylation processes are. And so looking at the mechanism of this reaction, they found, studying this in a stoichiometric sense, that they were able to take the starting rhodium-1 complex here, and as Camille helped us out with, this anionic rhodium complex is pretty nucleophilic, and so it can just directly attack these unencumbered electrophiles such as methyl iodide and undergo oxidative addition to form these rhodium-3 species. And all of these species were characterized in the case of this study by a combination of IR or NMR. And so after undergoing oxidative addition, this rhodium methyl complex will quickly undergo the 1,1 insertion to form the rhodium acyl species. And if kept at low enough temperature and in the absence of additional CO, these rhodium acyl species will actually dimerize and can crash out of solution. And that allowed for the characterization of this rhodium acyl dimer to be characterized by X-ray. So this was a pretty huge finding for this process, as they could now independently verify many of the proposed intermediates in the catalytic cycle. And so although this top line here is not done under catalytically, I guess, relevant conditions, as there's no CO or water, if you add CO to the acyl complex here, you can promote coordination of the carbon monoxide to form the catalytically proposed intermediate, and at low enough temperature, this indeed can be detected by NMR. This process is reversible, and the CO can be ripped off simply by applying vacuum. However, this this acyl rhodium 3 complex here at the bottom, while it is stable at low temperature below 0, if you simply warm it up to room temperature, you affect the reductive elimination of the acyl iodide. And so this mechanistic study really really helped support all of the key proposed intermediates that Camille helped us out with earlier. And so while now we have a good understanding of how this reaction works, does anyone want to propose what mechanism for oxidative addition might be operable here? If you remember back from the oxidative addition lecture, we have a few options of SN2 type, concerted, 3-centered, electron transfer. Eleanor, you're next on the list. Do you want to hazard a guess at this one?
I'm not sure. Maybe just SN2 type, if it works well with.
Yeah, perfect. As I've been hinting at, we have an anionic metal center that's relatively unencumbered, as well as an electrophile, which is a pretty good electrophile for SN2 type oxidative addition. And so indeed, that's the case where you simply get attack of the anionic rhodium on methyl iodide to form first the square pyramidal methyl rhodium 3 species, which can then undergo a rebound from the outer sphere coordinated iodide to form the octahedral intermediate here. And so one of another supporting factor for this was the fact that these anionic rhodium species are really key for the reaction to proceed at the rates that it does. If you simply swap the ligand sphere, and instead of having a strongly electron donating iodine, and you change that for these triphenyl arsenanes, which is an analog of simple analog of triphenylphosphine, which is also electron donating, the reaction proceeds 10 to the 5th times slower. And so that's a pretty huge difference by just simply changing one of the ligands. And so with this, they can sort of have a good understanding that indeed this is likely going through this kind of SN2 pathway, as you would expect something like this to maybe proceed through a different mechanism. And so the key, again, for this reaction and what allows it to take place so efficiently and quick is the fact that you have a unencumbered anionic rhodium species as the active catalyst. And so as you might expect, when you're, heating these simple rhodium catalysts to 180 degrees under, forcing conditions with HI and other additives, iodine, you might get some undesired side reactions. And because rhodium is one of the most expensive transition metals, the ability to recover it and reuse it in these processes is absolutely essential. So understanding these side reactions is crucial, and maybe in some cases even more important than understanding the mechanism of the reaction itself. And so they found one of the main side reactions of this reaction is the direct oxidation of this anionic rhodium-1 species by HI to form this tris iodine rhodium-3 complex. And then this is less soluble in the reaction media and crashes out, thus greatly slowing the reaction. And formation of this tris iodine complex can then lead to formation of a completely catalytically inactive tetraiodine anionic rhodium-3 species. And as you will probably know, because these are rhodium-3, they can't undergo the oxidative addition step to methyl iodide. And so they're completely catalytically inactive and thus need to be moved back onto cycle. And so one way that this is accomplished is to simply just use the water gas shift reaction, which we learned at the very beginning, to convert these rhodium carbonyl complexes back to rhodium-1 and get them back on cycle. And so unfortunately, one of the main drawbacks to this is if you want to promote water gas shift, you need to add, there you have it, you need to add more water. And as you might imagine, the separation of water from acetic acid on industrial scale can be quite a problematic and expensive process. And so because all of these processes are simply rendered useful because they can be done so efficiently, the added expense of water removal can oftentimes make this impractical if you need anhydrous or near anhydrous acetic acid. And so the way that would work is, or the way the water gas shift is used in this sense, or in this case is the, like Tuhan showed us in the beginning, is first promoted by attack of water onto the carbonyl ligand. This is followed by decarboxylation and then reductive elimination of HI to form your catalytically active species and HI. And so while this works great, again, if the goal is to make anhydrous or near anhydrous acetic acid, this is slightly problematic and other workarounds need to be used. And so as you might imagine, as this process, as Camille helped us in the beginning, this process can reductively eliminate an acyl iodide. And this acyl iodide need not inherently react with water if there is no water present. And so the Eastman chemical company developed a similar process based on this technology called the Eastman acetic anhydride process. And so here we have the key intermediate that Camille helped us with earlier, whereupon we undergo that key reductive elimination step to form the acyl iodide. And so now this acyl iodide in anhydrous conditions can react with either acetic acid that was formed or with lithium acetate to directly form acetic anhydride and the HI promoter or lithium iodide, depending on if it gets attacked by lithium acetate or acetic acid. And although this complex, this catalytic cycle is much more complex in the sense that you have now you have acetic anhydride floating around as well as these, as well as acetic acid and lithium acetate, as well as methacrylate, the main catalytic cycle still remains the same. However, the main, I guess, off of the catalytic cycle, the main organic reaction, namely the condensation of the acyl iodide with acetic acid or acetate is different. And this process allows for efficient production of acetic anhydride using the same conditions, essentially, that is used for Monsanto process. And so, as I mentioned in the beginning, Monsanto developed this process in the 1970s. However, it still was not exactly perfect. And so BP later developed in I believe 1990, what is known as the Cativa process, which has largely taken over and completely replaced the Monsanto processes. And I believe in many cases, actually, they just directly used the same reactors that they had been using for the Monsanto process for these iridium catalyzed processes. And as the rate of reaction is incredibly important for industrial chemistry, this reaction is able to occur around 5 times faster, which, although it's not huge, is still considerably more. Additionally, depending on market prices, iridium can actually be a lot cheaper than rhodium, which is interesting considering typically the third row metals are more expensive than their second row analogs. And so this was great for both those reasons, and they were able to make this, make acetic acid in an even cheaper fashion. However, the iridium process is much more complex because as iridium is a third row transition metal, it's able to more readily adopt some higher oxidation states under these, what I would consider highly oxidizing conditions. And so although I won't work you through the complex network that is the BT Cativa process, I'll just note that it shares many similarities to the Monsanto process. And we'll sort of go over 2 of the main differences which explain why this process is allowed to occur in a more efficient fashion. And so first, similar to the Monsanto acetic acid process, you start with this anionic M1 center. And this is able to undergo oxidative addition. And so in the case of the BP Cativa process, iridium is able to undergo oxidative addition 150 times faster than rhodium. And although you might be looking at this and slightly puzzled, as you might expect that a lower transition metal will undergo oxidative addition faster, they attribute this the faster oxidative addition of iridium compared to rhodium to the increased metal bond strength, MC bond strength in the product. So as you'll note, you are forming a metal carbon bond, which should be expected to be stronger for the third row compared to the second row. And additionally, as I alluded to for the mechanism, these third row transition metals can more readily adopt higher oxidation states and are typically stabler in higher oxidation states. So for these reasons, they attribute the faster oxidative addition of the anionic iridium compared to the anionic rhodium. However, now that we have this anionic rhodium or iridium-3 methyl complex, we need to undergo the key CO migratory insertion step. And so, Kelly, do you want to help me out as to whether you think iridium or rhodium will be faster at this process? And so using this same, using these, I guess, findings here, how would you rationalize which one is faster?
I guess I'm not sure how to think about that logic in relation to this.
So if the iridium methyl bond is stronger than the rhodium.
Okay, so then this process should be slower with iridium.
Exactly. And so in this case, although the first step of this sequence, which is the oxidative addition, which can be rate limiting for rhodium, now, although you're picking up a faster oxidative addition complex, now the CO migratory insertion, the selectivity switches. And as Kelly said, the rhodium one, because the rhodium methyl bond is weaker, undergoes faster migratory insertion. And so a key breakthrough and what really allows this process to occur at relevant rates is the use of this key promoter, the ruthenium tetracarbonyl diiodide. And so this ruthenium 2 promoter, it's again used in catalytic amounts and recovered at the end of the process and reused, happens by the abstraction of an iodine from the iridium center after this oxidative addition. And so now if we abstract an iodine, we can get to this neutral complex here. And so Kelly, do you want to help us out again here with which iridium species you think will undergo a faster CO migratory insertion? And in this case, as you can see, this happens, one of these happens 700 times faster. And so this makes up for the, although the iridium migratory insertion is typically slower, the use of this promoter can really allow this to take place quite quickly.
So this should be the one on the right would be faster.
So this one is indeed faster. And do you have any guess why that might be?
Does it have to do with the formal the formal charge on the complex being neutral rather than negative?
Yes. So the charge is, as you can see, the major difference in this complex. And so if you have an anionic charge here, or an anionic metal center here, that will also make your metal center more electron rich. And these CO ligands will make it more electron poor. And so if you have a more electron rich metal center, is that going to strengthen or weaken your metal carbonyl bonding?
That will, sorry, on the more electron rich metal center.
Sure. So I think it's yeah, go on.
Weaken the bonding?
So if you have a more electron rich metal center, that will weaken your bonding with CO based on what? Why would that happen?
Oh, sorry. Would it strengthen it because you have more back bonding?
Perfect. And so in this case, you have a much stronger iridium CO bond because you have this anionic charge, as well as having 3 iodines coordinated. And so this is one of the major factors that contributes to why the neutral one proceeds much faster. In addition, although this need not be true in all cases, generally electron poor metal centers undergo migratory insertion faster. And so because you have a stronger iridium carbonyl bond here, and you have a more electron poor metal center here, this one is going to go much faster. And so indeed what happens in the case of the BT Cativa process is this oxidative addition complex then has an iodine abstracted by the ruthenium promoter here in exchange for a carbonyl ligand to make this relatively electron rich iridium 3 into now an electron poor iridium 3. And this is key for, again, allowing the migratory insertion and reductive elimination. And so here we've sort of gone through in warp speed the BP Cativa and Monsanto acetic acid process. And now we're going to move on to a little more complex chemistry where we have more than just C1 building blocks. So we'll start from, I guess, a historical perspective in the sense that the cobalt hydroformylation, i.e. the reaction of CO and alkene and hydrogen to produce an aldehyde, was discovered before its now ubiquitously used rhodium process. And so this process was originally discovered, again, by the German chemical superpower BASF by Otto Rowland in 1938. And in this case, he was not looking to discover hydroformylation, but instead was just studying the effect of alkenes in the heterogeneous Fischer-Tropsch process, which is simply the reaction between CO and H2. And so he was doing this and found, actually after some metal leaching from the heterogeneous cobalt leaching into solution, that he was getting out some aldehydes. And so this was quite puzzling, however, was potentially useful. So they later discovered that this process could be run with the homogeneous catalyst cobalt carbonyl under extremely high temperature and pressure. And so the active catalyst, the cobalt monohydride here, is formed directly by the reaction of the bimetallic cobalt carbonyl with hydrogen in a sort of bimetallic oxidative addition. And this cobalt hydride is particularly acidic, as Curie had mentioned in the beginning of his talk. The MH bonds can vary drastically in their hydricity and H dot donor abilities and acidity. And so these particular cobalt hydrides are quite acidic. And so what the catalytic cycle looks like for the cobalt catalyzed hydroformylation is first, after the bimetallic oxidative addition to form the monometallic cobalt hydrides, you will dissociate a equivalent of CO to open up a coordination site, which will allow you to bring in an alkene here. And so after you lose a carbonyl and pick up the alkene ligand, you can undergo two processes. First is the insertion of the cobalt hydride to give the terminal metal alkyl species, and the other would be to give this species in a branched fashion where the cobalt is at the internal carbon. And so this process is reversible simply via beta hydride elimination. And so this internal metal alkyl species is less stable and can go back onto forming your on-cycle species. However, this off-cycle species is also stable enough to then go on and complete the catalytic reaction and give you the undesired branch selective hydroformylated product. However, for this, in this case, we'll just focus on the main on-cycle reaction, which is the formation of the linear aldehyde. So after formation of this cobalt alkyl species, you can then readily coordinate another equivalent of CO. Sorry, the garbage truck is outside. So then after formation of this tetracarbonyl cobalt alkyl species, you then undergo the next elementary step. And so let's see, Alex, do you mind hazarding a guess as to what we're going to form here?
Will you have like migratory insertion of a CO?
Perfect. And so we get migratory insertion of the CO here. And now we have this cobalt acyl species, which we have seen before in the case of our Monsanto process. And so we undergo the CO migratory insertion into the cobalt alkyl species. And now this is determined to be the resting state of this catalytic cycle. And so now we have I guess, three other things that can happen in this cycle. With the open coordination site, what do you think is going to happen in the on-cycle case?
I guess at some point you need a hydride, right? So can you have H2
Exactly.
added?
So how is H2 going to add in this case? What
Like,
elementary step?
is it oxidative addition, or it will just stay as like a 2 center 3 electron?
Yes, your first guess was right, and we get oxidative addition of hydrogen to form the dihydride. And then can you finish off the cycle here? What are we going to get out as the product?
You just need reductive elimination to get your aldehyde product.
Perfect. So reductive elimination gives us the linear aldehyde and regenerates the cobalt monohydride. And so, as you might imagine, you have these two other things, CO and alkene, floating around in solution, and some of them may be actually easier to react with this unsaturated cobalt center. And so can you predict maybe what one of the main off-cycle species would be here?
So if you have the alkene coordinate, and
You
then
could
you
have the alkene coordinate.
and of course the other option is to have the CO coordinate, but I guess with the alkene.
And why would you expect the alkene to be coordinate more readily than the CO? I'll give you a little hint here. We're running this reaction at 200 to 300 atmospheres of CO.
Oh, so it would just come back off.
Yeah, so in this case, because these reactions are run at such a high pressure of CO, typically the main off-cycle species is this tetracarbonyl rhodium acyl. And so by coordination, preferential coordination of CO over oxidative addition to H2, you can sort of just sit here with this off-cycle species. And then this can simply be brought back on by loss of CO and oxidative addition of H2. And after the oxidative addition of H2, the process is no longer reversible, and this irreversibly goes on to form product. And so unfortunately, as I mentioned, these processes with cobalt need to be run at extremely high pressures of CO to prevent decomposition of the catalyst. And so although the reaction is negative order in CO, the pressure of CO needs to be so high to prevent decomposition at the high reaction temperatures. And in these cases, with a non-ligated cobalt, you typically get a linear to branch ratio of 4:1, which is at least acceptable for some processes. And this mechanism was originally proposed by Heck and Breslow in the 1960s for the cobalt process. And they actually did a pretty good job and got it almost spot on for what I have drawn up here above. However, due to the high required pressures of CO and the relatively low linear to branch ratio, people set out for a more improved process. And then the Shell company found that you could add bulky phosphine ligands to help improve selectivity and allow the process to occur at a much lower pressure, which just makes it more friendly on an industrial scale. And so they first found the use of tritert-butylphosphine. They have a higher linear to branched ratio at something that is a more realistic pressure. Unfortunately, this process has a variety of advantages and disadvantages. First being that p-tert-butylphosphine is also volatile, and in order to be recovered, can often get leached into the product. So Shell then switched to this use of a similarly bulky phosphine. However, this one has a very high molecular weight, so is not eluted out in the distillation of the aldehyde product. And so this will stay in the reaction vat and you won't get appreciable loss of phosphine ligands. And so one of the main advantages of this process is that you strengthen the metal carbonyl bond, which then allows for lower pressures and less cobalt decomposition at lower temperatures or at high temperatures. And so that's really good. You can improve all of these aspects. However, there's of course a trade-off, which is because you're strengthening the metal carbonyl bond, your rate will go down considerably, as we saw in the case of the iridium versus the rhodium case. When you strengthen your metal carbonyl bond, you typically make margatory insertion slower. Additionally, because you now have a phosphine coordinated, you will get additional side products such as direct hydrogenation of the alkene. Additionally, you can also get direct hydrogenation of your aldehyde product, which can be a downside if your end goal is to isolate the aldehyde. However, if you're going to carry this out as a one-pot hydrogenation to the alcohol, this can actually be an advantage. And indeed, Shell uses this process in combination with the shop process, which is the production of higher molecular weight alkenes from lower molecular weight alkenes via metathesis. So in this case, Shell produces these octenes or dekenes as a mixture of regioisomers, and then is able to use this cobalt phosphine system to chain walk the alkene and produce a linear alcohol, which results from the hydrogenation of the aldehyde intermediate. And so this process was developed by Shell, whereupon they can just simply use this mixture of alkenes that they produce from shop. This is done at relatively mild conditions, and they're able to produce these linear alcohols, which result from direct hydrogenation of the aldehyde product form. And so, although this cobalt process is nice because cobalt is much cheaper, eventually this hydroformylation on an industrial scale has almost completely been replaced by the rhodium catalyzed hydroformylation. And this was discovered slightly later in 1970s by Pruitt at the Union Carbide Company. And this can take place at much lower pressures, making it more friendly to design plants. And most importantly, it occurs at 3 to 4 orders of magnitude faster. And so although rhodium is approximately 3 to 4 orders of magnitude more expensive than cobalt, because it occurs much faster under friendlier conditions, and because rhodium is much easier to recover than cobalt, this process has largely phased out its cobalt, the former cobalt catalyzed process. In an unsupported rhodium center where you just have carbon monoxide and hydrogen, this process provides, however, no selectivity for linear versus branched. However, they found the addition of triphenylphosphine, excess triphenylphosphine, can really drastically affect this process. And I'm not going to go through the whole catalytic cycle of the rhodium catalyzed process, as all of the elementary steps are essentially the same. However, due to the addition of multiple equivalents of phosphine, you make the coordination environment of rhodium extremely complicated and hard to deconvolute throughout these processes. And so I drew these species up here to show all of the potential rhodium hydride phosphines that you could form in solution. And so as you can see, this is these species are all in equilibrium. However, as you might expect, one of them is expected to be the most active and or selective. And so I've highlighted here the rhodium bisphosphine complex, which is sort of the perfect balance between reactive and selective for the linear aldehyde. And so typically as you add more phosphine, you can get a more selective process and give the linear product in higher yield. However, these processes are too sluggish to be viable industrially. So typically this phosphine is the, I guess, acceptable and desired species. If you lose phosphine, like I had mentioned, simple unsupported rhodium carbonyl species are extremely reactive, however, give no selectivity. And so because of the difficulty of separation of regioisomers, this sort of unsupported rhodium system is not really practical unless you're using ethylene, where you cannot have regioisomers. In addition to the complex network of how many phosphines are coordinating, you additionally can have a mixture of both the facial, or I guess what you would consider the equatorial coordinated, as well as this coordination environment for the bisphosphine. And this can be determined by NMR to be in equilibrium with about an 85:15 ratio of the desired equatorial coordinated bisphosphine. And so this has spurred a sort of huge interest in developing a bisphosphine ligand that would be able to not only prefer being coordinated as a bisphosphine and not promote coordination of higher numbers of phosphines or complete dissociation, but also one that could be locked into this equatorial fashion, which is the species that was determined to give the high selectivity. And so if we quickly look at the expected dihedral angles between the ligands, we can see that if these two phosphines are in the equatorial position, they'll have approximately 120 degrees in between them. However, if one of these phosphines swings down, this bond angle will be approximately 90 degrees. And so in the case of using a chelated phosphine where these two are tethered together, you might expect that you can effectively design a ligand with the proper bite angle that would prefer to be something around 120 degrees versus something at 90 degrees, and therefore favor this equatorial coordinated rhodium bisphosphine. And I guess fortunately this worked out really well, and they were able to design these very wide bite angle bisphosphines, such as this one here, Bisbee, with a bite angle of 113 degrees, and this gives a whopping 66:1 linear to branch ratio, which was much greater than any of the previous triphenylphosphine systems. And just to show you how this works, if you change this bisphosphine to something closer to the 90 degrees, you get almost no selectivity, as you disfavor coordination in the equatorial plane. And you can extend this chelating phosphine out slightly, and you can slightly improve your selectivity. However, it's really these huge bite angle bisphosphines, such as Bisbee or Xanthos, that give this really good selectivity. Unfortunately, I don't think we have time to really go through the problems of the day here. So I think we'll have to wait on those for next time. Sorry, my mouse went a little crazy here. And so, as you might imagine, these processes, because they occur so efficiently, have been used in industrial processes beyond simple functionalization of N-hexenes. And there has been numerous applications, namely in the fragrance industry, as many of you know, aldehyde compounds can have some pleasant smells. Typically, there can be sweet smelling, and so due to the easy access to terpene starting materials that have, an alkene that can readily be hydroformylated, there's a huge amount of applications of hydroformylation using the rhodium system in the fragrance industry, where you can take something such as limonene and hydroformylate it, and now you have a completely new fragrance compound. Additionally, as you may note from things like limonene, these types of 1,1 disubstituted alkenes can be hydroformylated in an enantioselective fashion, which would potentially expect to give different smells. And so there's one example where the asymmetric hydroformylation of a 1,1 disubstituted alkene can produce this fragrance compound known as Florhydral, which, although happens in low EE, is still enough to give the desired smelling enantiomer. Although you might expect hydroformylation to be used in industrial synthesis of drugs because it happens so efficiently and with such low loadings of rhodium, and sort of uses very cheap materials, namely CO and H2, and produces an aldehyde, which is an extremely useful intermediate. There's seemingly few examples of this in the patent literature. And I think one main reason is the above examples we see, which produce relatively cheap chemicals compared to more, I guess, value-added products such as drugs, is those cheap chemicals are all very low molecular weight and can easily be distilled or just separated by a biphasic extraction. However, in the case of drugs, your structure is often much more complex, and separating your product from rhodium can be extremely difficult. And so I guess one of the major applications of this process still in use is the synthesis of vitamin A, shown here by BASF, where they simply form this intermediate aldehyde, or where they form vitamin A through a Wittig reaction using the synthesis of this aldehyde using the hydroformylation scheme. And I've sent out this paper in the email if you're curious to read more. And so it looks like we're narrowing in on time, so I'll try to blow through this section as quick as possible. As I alluded to earlier, the prospect for enantioselective hydroformylation was really intriguing and people were really excited about it, especially for syntheses of these types of valuable drug compounds. However, due to the problems I mentioned, they really haven't been used industrially. And so two key factors that have allowed the development of enantioselective hydroformylation catalysts is either substrates with electronic activation that can preferentially give branch substrates such as these styrenes here, as well as ones that can be directed to internal positions, either through a directing group strategy or a transient directing group strategy. And naproxen and ibuprofen were first synthesized asymmetrically using hydroformylation by Stille with actually this platinum catalyst. However, as I mentioned, the commercial viability was impractical due to the high cost of the alkene or the styrene precursor, and also due to the difficulty in recovering the platinum. And so I've highlighted sort of two of the main families of asymmetric hydroformylation catalysts here. The one originally developed by the Nozaki and Takaya lab uses these interesting phosphine catalysts with these two axially chiral centers, and the relationship between these axially chiral centers is key for allowing the high EE. And another family of directed asymmetric hydroformylation as well as activated, developed by Clark Landis, where they use these what are called diazophospholine catalysts. Although you don't need to know the structures of these and you won't be on the exam, it's I guess just important to know the general structure and the types of substrates that you can asymmetrically hydroformylate. In case you were to be asked that, you would not propose a asymmetric hydroformylation of something like N1-hexene because you simply would just get the linear product. So using these directing strategies or electronic activation in the case of styrene, you can selectively get the branch product in good to high yield NDE. And so another strategy used, as I had alluded to earlier, is a transient directing strategy. And in this reaction developed by TAN, the amine undergoes a condensation with the transient directing group to form this now directing phosphine intermediate. which can coordinate to the rhodium and allow for the asymmetric hydroformylation of these internal alkenes. I think we'll have to wait on the, I can just start by introducing the last two topics that I think we're quickly ran out of time here. So the last two topics are sort of elaborations of hydroformylation, and that they involve this kind of migratory insertion step. However, instead of reductive elimination with CO, they can undergo a different set of sequences. So in the case of hydroaminomethylation, which was again developed by the German chemical superpower BASF by Walter Riep in the 1950s, this process simply uses a dual organic reaction combined with hydroformylation, whereupon you hydroformylate your alkene, undergo condensation with an imine in the same pot, followed by imine hydrogen to give your linear selective alkylamine. And so I think with that, we'll let you go so you can watch the defense, and we'll cover the last section, which is just the hydrocarboxylation, maybe after the exam.
So we're going to go over the problem of the day for the catalytic carbonylation lecture. So for the first problem, you see we have a linear aldehyde here, and then a structural isomer, the branched aldehyde here, B. And the question is asking, how is this process reversible, and draw a mechanism. So first, let's look at the catalyst we're using here, CP star rhodium propene, bispropene. And so as we can tell, the ligand here, propene, is also a constituent in the product A and B, and so that might be helpful. Additionally, if we think about CP star as a ligand, we might not expect that to be particularly effective in controlling one regioisomer over the other. And so even if you don't know that, just based on the distribution, you should be able to assume that something like that will be possible. So let's get into the mechanism here. So first, the reaction starts with rhodium 1 here, coordinating to the propene ligand and undergoing an oxidative addition to the CH bond of the aldehyde. We've gone over this elementary step as the crucial part in the Tsuji-Wilkinson decarbonylation reaction. However, unlike the Tsuji-Wilkinson decarbonylation reaction here, we have another alkene in solution. And so instead of directly undergoing the decarbonylation followed by CH reductive elimination, it's actually much faster to directly insert the hydride into the alkene. And that can again give either linear or branch selectivity. So if we form the linear selective compound 10, that will sit there and eventually undergo decarbonylation to form the compound 3, which is the both linear alkyl carbonyl complex. And this will just sit here and is a resting state. It's not really going to be productive in this transformation. So let's move back on cycle, and we go from 9 to 10 prime, where we insert with the opposite selectivity to give the secondary alkyl rhodium species. Now that we have the secondary alkyl rhodium species, you can imagine a variety of things. Well, for one, you could get direct CC reductive elimination. However, that's not as fast as 1,1 migratory deinsertion, and so you'll undergo the decarbonylation to form 3 prime. Now this can either reinsert CO into the linear species or the branch species. And indeed, some of it will insert into the branch species to form rhodium acyl complex 10 double prime. And then you can take home the rest of the catalytic cycle here by by beta hydride elimination from 10 prime, and then fast CH reductive elimination from 9 prime to form your isomerized aldehyde. And one of the key things to note here is when you look back to the beginning of the cycle where you're forming 9, you don't have a rhodium alkyl species to directly undergo CH reductive elimination. And this is key to preventing the undesired Tsuji-Wilkinson decarbonylation, because if you form a rhodium-3 alkyl hydride, the reductive elimination is expected to be extremely fast and irreversible. And so if you're drawing this catalytic cycle and at any point you see yourself with a cis-oriented rhodium-3 alkyl hydride, and you're not invoking reductive elimination, you might want to go back and think about how you could potentially get rid of the hydride before that to prevent this from happening. So the main takeaway here is that you need an accepting alkene to take the hydride right from the start. Otherwise, you'll get undesired Tsuji-Wilkinson. And so for question 2 now, let's look. We just basically need to make B from A using only C1 feedstocks. And so we know based on today's lecture, one of these is going to have to be a carbonylation reaction, probably hydroformylation. And so starting from the feedstock A, crotonyl acetal, this will directly undergo a chain walking hydroformylation to give the linear selective product. And now this aldehyde is a versatile intermediate, and you could probably draw multiple ways to the product. However, the most straightforward way to synthesize alpha amino acids from aldehydes is the Strecker reaction, and so that's what we're going to do here, where we'll condense the aldehyde with ammonium hydroxide to form the imine, which can then be attacked by the cyanide to form the aminocyanide. And this will undergo easy hydrolysis to form racemic B. And although it's not included here, although it should be on your handout, you'll see they complete the synthesis of the enantiopure by enzymatic resolution of the CBZ protected amine.